The electricity generated inside a hydropower station isn't delivered to you in the same form. Sometimes it is transformed into extremely high voltage AC, and sometimes it is converted into DC. Then, just before it reaches your home, it's changed yet again. Why would engineers convert electricity back and forth multiple times? Every single second, billions of watts of electricity travel hundreds, even thousands of kilometers before reaching your home. Today, we are following a single electron journey from a hydropower generator all the way to your light switches. So everything begins inside the powerhouse. A turbine spins at hundreds of revolutions per minute. That spinning shaft rotates a massive generator. Inside the generator, a powerful magnets rotate past stationary copper winding. This moving magnetic field induces electricity according to Faraday's law. The generator produces three-phase alternating current, typically between 11 and 25 kilowatts. But although thousands of volts sound enormous, this voltage is actually far too low to send electricity hundreds of kilometers. Imagine trying to move an entire lake through a drinking straw. The energy would be wasted before reaching its destination. So electricity behaves in a similar way. If we keep the voltage low, the current becomes very high, and the high current creates heat. That heat wastes enormous amount of energy. So engineers solve the problem with one incredible machine, the transformer. Right outside the powerhouse stands the step-up transformer. Its only job is to increase voltage. For example, 11 kilowatt become 220 kilowatt or 500 kilowatt or even 765 kilowatt. In China, some transmission line operates at an astonishing 1100 kilowatt DC. But why raise the voltage so dramatically? Let's imagine the power plant must deliver 100 megawatts. At low voltage, the current is extremely high. At high voltage, the current drops dramatically. And because transmission losses depends mainly on current, reducing current drastically reduces energy losses. This is why high voltage transmission is so efficient. Instead of losing electricity as heat, almost all of it reaches its destination. The electricity is now ready to begin its long journey. Most countries use high voltage alternating current for transmission. After leaving the transformer, electricity enters enormous steel towers carrying three conductors. These lines cross mountains, rivers, deserts, and entire countries. Electricity doesn't stop at one city, it follows through an interconnected national grid. Think of it as a gigantic highway system. Every power station feeds electricity into this network, and every city draws electricity from it. If one power plant suddenly shut down, another can immediately supply power through the same grid. This makes the electrical system remarkably reliable. But electricity cannot remain at hundreds of kilowatts forever. Before entering cities, the voltage must be reduced. The first stop is the grid station. Huge transformer reduces voltage step by step. 500 kilowatt becomes 220 kilowatt. 220 kilowatt becomes 132 kilowatt. 132 kilowatt becomes 66 or 33 kilowatt. Notice something interesting. Engineers don't reduce the voltage all at once. Instead, they decrease it gradually. Each state feeds different part of the network. Large industrial area may receive 132 kilowatt directly. Medium industries may use 33 kilowatt. Only residential areas continue to the next stage. Next comes the distribution substation. Here, the voltage is reduced again, usually from 33 kilowatt to 11 kilowatt. These 11 kilowatt feeders spread throughout towns and cities. You will often see them mounted on concrete or steel poles. Factories located nearby sometimes receive this 11 kilowatt supply directly. They install their own transformers depending on their equipment. Residential neighborhood continue one step further. Near your street stands a familiar gray transformer mounted on a pole or inside a green metal enclosure. This is the final transformer. It converts 11,000 volts into 400 volts 3-phase or 230 volts single phase. Finally, electricity enters your service cable, passes through the energy meter, flows into your distribution board through circuit breakers, and reaches every light, fan, television, air conditioner, and charging socket inside your home. The journey is complete. At this point, you might ask, if electricity keeps changing voltage, why not simply generate it at required voltage? The answer is transformers. Transformers work only with alternating current. They are simple, reliable, efficient, and capable of changing voltage with efficiencies above 99%. Without transformers, modern electrical grids would be almost impossible. That is why AC become the world's dominant electrical system. But there is one exception. When electricity must travel incredibly long distances, that is where DC becomes the better option. Imagine sending electricity 3,000 kilometers. At these enormous distance, alternating current begins to face new problem. Long transmission line behaves like joint capacitors. Reactive power increases, grid synchronization becomes difficult, stability decreases, losses increases. Instead of fighting this problem, engineers use a completely different approach. High voltage direct current, or HVDC. Here's how it works. The generator still produces AC. Nothing changes inside the powerhouse. But after the step up transformer, electricity enters a converter station. Here, power electronics convert AC into DC. The DC voltage may reach plus minus 500 kilovolt, plus minus 800 kilovolt, or even 1100 kilovolt. Now, the electricity travels hundreds or thousands of kilometers as direct current. Because DC has no frequency, no reactive power, and lower transmission losses over long distances, it becomes extremely efficient. When it finally reaches the destination, another converter station changes the electricity back into AC. Only then does it rather enter the normal AC grid. To homes, to factories, and business, nothing looks different, and they still receive ordinary AC electricity. Japan has the one of the world most fascinating electrical system. The eastern half operates at 50 hertz, while the western half operates at 60 hertz. The two systems cannot simply connect together. It's like trying to connect two engines spinning at different speeds. Instead, special HVDC frequency converter stations act as a translator. Electricity arrives as AC, it converts into DC, they convert back into AC at the other frequency. This allows power to move between eastern and western Japan whenever required. Without this converter station, sharing electricity between the two regions would be nearly impossible. China has built the world's largest HVDC network. Many of its biggest hydropower stations are located deep inside western China. Meanwhile, its largest cities lie thousands of kilometers away in the east. Transporting such enormous amount of power using only AC would be inefficient. Instead, the electricity follows this path. Hydropower station generator produces AC. Step up transformers, then converter station AC become DC. Ultra high voltage DC transmission line receiving converter station DC become AC again. Then the normal AC distribution system begins. Grid substation, distribution substations, 11 or 10 kV feeders, distribution transformer. Finally, 400 or 230 volt arrive at homes and industries. China's longest HVDC project transmit several gigawatts over distances exceeding 3,000 kilometers with remarkably low losses. Many people assume DC would be better because batteries and solar panels use DC. But there's a major problem. Changing DC voltage isn't simple. AC transformers are incredibly cheap, efficient, and reliable. DC requires complex electronic converter. These converters are expensive, generate heat, require cooling, and increase maintenance. Since almost every existing appliance and electrical grid was designed around AC, it remained the most practical choice for local distribution. That is why nearly every home on earth still receive alternating current. So the complete journey looks like this. Water spins a turbine, the turbine spins a generator, the generator produces AC, a transformer increases the voltage, electricity travels across the country, and if the distance is extremely long, it may be converted into DC. After reaching its destination, it's converted back into AC, the voltage is reduced step by step through substation, distribution transformer, service cables, meters, circuit breakers, and until finally it powers the light switch in your room. A journey of thousands of kilometers completed in a fraction of a second. And the next time you flip a switch, remember you're witnessing one of the greatest engineering systems ever built.